Okay, lecture 8 of our semester. Okay, let's go to our second homework announcement. So, at the last of our previous lecture, we have introduced the concept of sheet resistivity. So, I told you that resistivity is something like a three-dimensional quantity. At a given position, we can define the resistivity. But sheet resistivity, what is it? It is seen from the top of your wafer. So, for example, let's say that you have drawn a line of doped semiconductor, and here, for example, let me just draw something. Now, here at this part, you have introduced a metal contact. This is a metal contact, and here also you have introduced a metal contact. Yes, they should be treated as a metal contact, but in between them, you have introduced, in this case, three serially connected squares. So let's assume that this length and this length, they are the same, so it is a square, and we have placed three squares. So now you understand this is corresponding to three squares, and it will show certain resistance R. Yes, you may have it. But instead of that, now let's assume you have just widened this system. So instead of this single line, you just double the structure. So these red colored boxes are newly added, but still you have metal contact and now you have a metal contact. Then what will happen? Now you have 6 squares. However, their alignment is along the transport direction. Now you have 3 squares, and along the direction perpendicular to the transport direction, you have 2 squares. My question is, compared with this original, the resistance R, if you introduce 3 times 2 squares in that way, then what will be the expected the resistance? The resistance would be just half of original one, because now the channel to conduct the electrical current is just twice wider. So you can understand this is the case. However, even though you have spent exactly same number of 6 squares, if you introduce in that way 2 by 3 way, here you have your metal contact now, and here you have your metal contact now. If that is written in that way, then what will happen to your resistance? It will be further reduced, because now the distance becomes even shorter and width becomes even longer. So you must travel shorter distance with more electrons. So now you can understand the resistance, the observed resistance by your system can be written as certain things like this. Just number of squares between your two contacts. So it simply means that if you have a long distance between your two metal contacts, if this length is long, then your resistance will be higher. And simply, once again, if width becomes wider, then the resistance will be reduced linearly. So by using this one, you can easily understand there occurs certain number like L over W, not exactly only L, not exactly only W, but the ratio is important. Now let's assume a case of ratio equal to 1. What does it mean? So it means that yes, this is corresponding to the case of your ratio 1. Yes, now you can expect a certain resistance between this and that point. And now let's consider a little bit wider square between this and that. So what will be the resistance? If this one has a resistance R, then what will be the resistance of this square? This simple expression shows that it is corresponding to the same value R. If you have just a unit square between your two contacts, then regardless the length of your each line or each edge in this square, whether that is long or short, but regardless of their actual size, it is just given by the number of squares, not exactly the size of it. Of course, I'm not, please don't be confused by this one. So now let's say that you have a small square and you have a wider square, and this argument just to assume that your contact, metal contact located here and there also now let's consider this case. In this case, it is certain that the resistance seen by this system would be much higher than the resistance seen by this small system, because you know, when you have small amount of contact here, actually although you have a square, what is the actual active region of your doped semiconductor? Where can you find the actual conducting channel? Yes, only this part should be regarded as conducting part, and although we have tons of electrons here, but it does not contribute actually much to the resistance or conductance. So when we say sheet resistance is proportional to the number of squares, actually the number of squares along that transport direction, it just assume that we have placed our contacts in a reasonable way, not in this weird way. I mean that this one would be quite a weird way to place our contacts. So therefore, let me just come back. Our homework number 2, just to assume a special case like this. So let me just draw once again. In this case, in this example, Z direction, that shows the vertical direction perpendicular to the wafer surface. So let me just draw. Okay, so I'm saying that this is your Z direction. And what is the origin of your Z direction? Yes, this is Z equal to 0 plane. In this plane, here you may consider a plane. This plane is the surface of your wafer, and you place your contacts just on that surface. For example, in this case, you may draw your first contact here, and you may draw your second contact here. That happens. And where are two other coordinates, x and y. Of course, you can say that maybe this direction can be x. For example, this direction can be y. So this is the case. So now let's come back to our assumed electron profile. So it is exponentially decaying when we have deeper position. So when G increases, then it is exponentially decaying, and it follows the rate of decay delta. What is the delta? That is just numbers corresponding to nanometer or micrometer, depending on your doping concentration. So now you may think that if we visualize, sorry, so it is stuck once again. If we visualize okay, so if we visualize the electron density, then we have to write down in that way. Only surface region we have a lot of electrons, and if we change the position or point of measurement deep into the substrate, and the exponentially our electron density goes away. In that case, what will be the sheet density seen from our two contacts? That should be answered by your homework problem. Simply, that is related with the integration of your electron density, but please think about this one. And I wanted to give you a hint to solve this problem. Although we draw in that way, so sheet density here, in between these two contacts we consider sheet density, but I wanted to say let me just draw once again three-dimensional picture once again for your clear understanding. Now let's say that here you have a contact, and of course here you may have a contact. So you wanted to solve certain length scale L and certain length scale W. Yes, then after that you will try to do something. Okay, electron density exponentially decaying from this position, starting from NS, it is exponentially decaying. That will be your typical starting point. But please note that the sheet resistivity doesn't, in order to calculate the resistance between them, then first you may say, okay, I have to consider resistance between the contact placed on top, and after that at this starting point there can be a resistance, and of course we may have resistance originated from this square itself. And after that, once we arrive at the end of this box, after that we may have another resistance component finally up to this top surface. But what I wanted to say is, when we talk about the sheet resistivity does not consider any contribution from these contact access resistances. This sheet resistance simply consider only contribution from your square. It is now neglecting the effect of your top placed contact and this plane. Okay, so when you make or when you try to calculate your sheet density, please do not consider this kind of parasitic component. You may think just one-dimensional structure. So simply speaking, my answer is, when you solve this problem, then you have to consider this semi-infinite coordinate system for your z direction, but your x position just starting from 0 and your x position just ends at L, and you may say that your contacts are actually placed vertically to this x coordinate. Okay, then please try to calculate the resistivity between this point and that point. That is corresponding to the definition of your sheet resistivity. Okay, so now you understand the applicability or application area of this sheet resistivity is just squares, not the excess resistance for our contact region. However, in usual case, that resistance is much smaller than the contribution from our long line. So that's the reason why, as a good estimation, really good estimation, we may think just contribution from our sheet, our squares. Okay, so if you have any question, then please let me know. Then that was your homework number 2. Then now let's go to our actual lecture. So I took this example from Professor Chen Ming-Hoo's book. So sometimes I took some graphs or examples from Professor Chen Ming-Hoo and Niemann or Park. So they may be good references to your study. Anyway, this is a Professor Hu's example, and this is just a simple manipulation. Let's assume that you have hole density like 470 square centimeter per volt per second. So you have to understand, when you see this number, you have to understand, in this example we are assuming the highest value we can imagine in the silicon valence band. So this is really almost unrealistic value. So theoretically maximum value we can imagine. So in this case, so simply speaking, we are assuming a very good quality of our silicon sample. After that, we have applied the electric field 10 to the 3 volt per centimeter. So simply, in many cases, people write down in that way. You must become familiar with this unit scale. This is the usual numbers you will see, kilovolt per centimeter. And if you arrive at such a number, then how can you call it? That is just 1 megavolt per centimeter. But this, in this case, this level of electric field is not related with actually your transport. You will see this number, this kind of electric field, only between your silicon dioxide. I mean that. So here you have a source, you have a drain, and in between we may have parallel electric field. But usually in that case, the value of your electric field is just orders of several hundred or several 10 kilovolt per centimeter. That will be the usual level of your lateral direction electric field. And for this direction, along this vertical direction, now you have So since you have already studied the basic course, I just assume that all of you understand the MOSFET structure. Now we have gate and silicon substrate in between the level of electric field applied to this oxide region may be in the range of several millivolt per centimeter. So please understand the level of electric field. Okay, so simply speaking, when the silicon is accelerated by silicon's carriers are accelerated by the levels of kilovolt per centimeter scale electric field, it conducts. However, since silicon dioxide is so good enough insulator, even though we apply several millivolt per centimeter scale electric field, it does not conduct any electric current. Okay, so really silicon dioxide is, especially thick silicon dioxide, is really a good insulator. Okay, then now you understand we are considering quite small electric field, 1 kilovolt per centimeter. It is just meaningful value of our electric field. Then the drift velocity can be simply calculated by this number. How can you calculate this number? Just please try to evaluate this product between mu n and e. Sometimes you must do it by yourself, because unfortunately in semiconductor literatures many times length scales are not in meter scale. Unfortunately, that is written in centimeter scale. Sometimes some uneducated student makes a silly mistake by confusion between meter scale and centimeter scale. When you do that mistake once, then you will have the error like 100 times or 100th times differences. It's okay. It's too bad. However, that is just related with your meter scale. But in many cases, you have the area scale or volume scale. So when you make certain mistakes in this meter, cubic meter and cubic centimeter, then the error would be just 1 million times. So in many cases, we can see that the student's answer is 1 million times higher or 1 million times lower, because he or she just misunderstood the length scale, meter and centimeters. So please, I want to strongly recommend, please do this calculation by yourself. So, and you may find that in this case the velocity is corresponding to 4.7 10 to the 5 centimeter per second. Then you have to understand also, you must have a feeling about this number. Is it high or is it low? Is it high speed or is it low speed? So fast or slow? Please note that the velocity we can achieve inside the silicon crystal by holes or electrons is just 10 to the 7 centimeter per second. Of course, here we have a leading number. However, this leading number is really close to number 1. So we cannot achieve, for example, 2 times 10 to the 7, 3 times 10 to the 7. It is very difficult to get in the semiconductor if we have a certain length scale. So compared with this one, this is just 5% of the maximum speed, so it is not that high. Why we have not that high speed? Because we have applied just moderate electric field to our material. So if we apply higher electric field, then of course our speed will be increased. Here we have some other quantity, momentum relaxation time. So momentum relaxation time simply assume that our whole mobility is given by momentum relaxation time divided by effective mass of our holes. So by calculating this one, tau is estimated as in the range of just 0.1 picosecond. Picosecond is corresponding to just 10 to the minus 12 second, 1,000th of nanosecond. So this is yes. How do you feel? Is it short or long? So if you are talking about the operation of your electronic device in just gigahertz range, then please think about gigahertz. Gigahertz is corresponding to 10 to the 9 hertz or per second. So its characteristic time scale is just nanoscale property. Your device is now operated in a gigahertz, or I mean that in nanosecond scale, but your momentum relaxation time is around just 0.1 picosecond. So it can be regarded as much shorter than the nominal time scale of your electronic device operation. So that's the reason why sometimes you may think that your electron gas or hole gas are somewhat close to certain equilibrium state, because it has very fastly moving electrons and holes, and something happens to your electron gas or hole gas, it is much faster. For example, you just apply certain pulse whose duration is, for example, in this case, just 1 nanosecond. If you have a pulse whose whose period is 1 nanosecond, then you will call it as this system is operated in 1 gigahertz clock signal. Then yes, this is 1 nanosecond, and this is corresponding to 1,000 picosecond. And you know that now your electrons and holes can react much faster than this one. Why I'm saying that? I'm just saying the momentum relaxation time, but why I'm saying that this is related to the reaction of our electron gas and hole gas. If you change your voltage drastically, suddenly, then what will happen? Inside your system, the electric field will suddenly increase or decrease. And by increase or decrease of your electric field, your electron or hole should have a new velocity. And in order to get new velocities or new state of carrier transport state, then actually it should suffer from several scattering mechanisms. And this 0.1 picosecond just characterize what is the expected average time scale between your one scattering and the next scattering. For example, if you have 0.1 picosecond as a momentum relaxation time, then roughly speaking, within 1 picosecond, your holes will see 10 times of scattering events. So if your hole takes 10 times of scattering event after 1 picosecond, yes, then its state will be relaxed to that dictated by a new electric field. So that's the reason why I'm saying that our momentum relaxation time is closely related to the ability to react with respect to newly built electric field inside this system. Okay, and of course, what I wanted to say, what I had to say in this case is, this is not the only relaxation time you have inside your electronic system. This is the momentum relaxation time, is the time to spend the relaxed momentum. However, your electron or hole may have other important quantity. Please think about this one. Another quantity it can have is energy. Energy is a somewhat different quantity. Then maybe you may guess, since both of them are relaxation time, maybe they have in a similar range. However, please think about this one. Usually when we say scattering, then we can consider two representative cases. One is, yes, that is scattering. In this case, it changes its momentum, and at the same time it changes its energy. We may think another one, yes, in this case our electron or hole lose its momentum, however energy is not lost at all. Please think about your high school physics. So now let's say that this is a really heavy particle, and you just send a small particle and make just collision. Then what happens? If it goes to in this velocity v, after collision, this small particle just reflected back, and it has a certain velocity. However, its velocity is actually the same. So when we just take the magnitude of this velocity, they are the same. So simply speaking, it changes its direction. The direction of their movement, its movement is completely different. So it is involved with momentum relaxation. However, it is not related with loss of energy. Energy is just kept as before. This is one thing, and this is usually called as elastic scattering. And now think about another one. Here we have one particle and one particle. They have quite a similar mass, and they are heading to each other and having similar mass and similar velocity. Then what will happen? They have a similar amount of momentums, and once they collide, then each of them will lose their own initial momentum, and even after that, since its speed is much, now something happens here. Then now this guy slows down, and this guy quite slows down. That can happen, and it is related with loss of energy. So once again, let's just come back to the discussion about scattering mechanisms. So here we can see that in elastic scattering, which is involved with energy relaxation, and elastic scattering, which is involved with just conservation of energy. So now, although there exists only one physical event called as scattering, but that event can be categorized into two parts. And if your electrons suffer from only by elastic scattering, then what will happen? Your momentum will decrease quite fast. However, energy will not be relaxed quite fast. If elastic scattering is the dominant mechanism of your system, then your electron just lose its momentum only, and velocity is just kept as before. So please think about the game called as the pinball. So you have certain elastic bumps, and when you just push a small metallic ball, then what happens? It is just hanging around this pinball game play, and it is collided too many times. However, it never loses its energy. Although its momentum is always changing, but it is still quite fast. That is typical case seen by this elastic scattering dominant system. However, if your system becomes inelastic, dominated by the elastic scattering, then maybe the momentum relaxation time and energy relaxation time will be in the similar rate. Then what is the actual situation of our silicon? Unfortunately, my answer is silicon, especially in conduction band, that is just 50-50. I mean, half of your scattering is dominated by elastic scattering, and half of them, roughly speaking, half of them are dominated by the inelastic scattering. So now you can see that not one scattering mechanism is dominant, and they are just mixed. Then please let's have a look at this one. Then what is actual physical mechanism underneath this scattering? Then the most important, or the first one we have to study in this class is phonon. So phonon is nothing but the thermal vibration of our crystal lattice. We are now assuming that there exists well placed, perfectly placed silicon atoms, and their positions are exactly periodically placed. However, due to the thermal excitation, although its average energy is determined by the crystal structure, but atomic cores can move slightly around their nominal position. So that is corresponding to the phonon scattering, because atomic cores are in many cases charged, positively or negatively charged. Or that in this case, in this silicon case, we have to say that that is positively charged, and our electrons, they are interacting. So if it is located at its nominal position, the potential generated by this silicon atom is already considered in our band structure calculation. That is understood. But if its position is slightly modified, then what will happen? The source of your attractive field is slightly modified, so the field seen by your electron can be also slightly modified. That is considered as phonon scattering. And phonon also has its own EK relation. So you know that we have already considered the EK relation of our electrons, but phonon can be also considered as a quasi-particle in this case. So now we can consider the energy versus K relation of our phonon, and you are now looking at the EK relation of a silicon phonon system. So actually, just like electron has quite complicated EK relation, phonon also has quite complicated EK relation. But in our actual consideration, please think about our silicon case. Although our our silicon conduction band actually have something like this. That was your X point, and this was called as delta. This is a delta line, and this is corresponding to 0.85 x. Here you have the minimum of your conduction band. After that, you have quite complicated behavior. I just have drawn the magnified view of our band structure nearby the minimum point. That is the general situation, but what we have done is, since most of our electrons are located only nearby this point, we just modeled it as a parabolic relation. So do you remember at the time we just introduced certain effective mass for our electron, and of course we have to understand this mass is not actually this scalar number but directional value. However, anyway, we just model only important points. Then now let's assume that where do we have important points in this EK diagram? So where do we have important ones? So these points, so you may find that some numbers or some labels. Those points are regarded as important points for our phonons. Why these points are regarded as important points? Because at those points your phonon is interacting with your electrons. Then it means that where can you find your electrons? Only this point. Then for example, can you see 0.3 in this case? This one is 0.3. Why do we have 0.3? If we have 0.3 in terms of our brilliant zone, please think about this one. Here you have 0.85 starting from gamma to x, and now this guy, the phonon whose momentum is given by 0.3, then they are interacting. Then what will happen? Please think about the number we can generate out of this 0.85 and 0.3. Of course, by adding them or subtracting one from the other, we can have 1.15, yes, or some other one, but that is not that important. Once we have 1.15, what is it? Since we are adopting the first Brillouin zone or reduced zone scheme, the value exceeding the range of gamma to x point, that should be just mapped and placed in a negative value. So what is it? So can you call it as just here we have a gamma point and x point, another x point, and we were here and the distance was just 0.15, and we add just number 0.3. Then where we are going now? We are going in this 1.15. Then in order to place this point once again back to our first Brillouin zone, we must take -2. So are you with me? Then that is just placed in that way. Then the final position becomes -0.85 measured from our gamma point. What is it? Is there anybody who can answer? Please note that this is the minimum point of your silicon conduction band. And what is this minus 0.85 point? This is another point for your silicon conduction band. Simply means that the phonon whose K value having 0.3 in the scale of our maximum K value in the first Boolean zone, it just to move one electron located in this valley to another valley located to the opposite direction. So let me just go to our other one. So it is simply like this. Here, let's say that there was one electron, and here the distance was just 0.15, and when we add 0.3, then it moves to this point. And this type of transition is typically called as G-type transition. And now you can see that so these phonons are related with G-type transition process. Okay, so also let me just continue. So now let's have a look at these 6 copies of your conduction minimum band. I just told you that how one phonon can move one electron from the top valley to the bottom valley in this drawing. However, we may think about other K values which moves one to the other 4 remaining ones. Where can you find the 4 remaining ones? For example, this one, this one, this one, this one cannot be moved by just adding 0.3. In this case, you have to have quite a high value or large value of your K value for your phonon. Then where can you find this kind of thing? This kind of transition is typically called as F-type transition, and this F-type transition can be placed in this position. So you know that in this case its value is almost close to 1, because it is just from the border of your Boolean zone to the another border of Boolean zone. No, the travel starting from this to that is not that long. This is not the right way, but their actual distance is just, yes, they are quite nearby. However, in the case of this F-type transition, they actually should travel quite a long distance in our K-space. So, therefore, from this discussion, we can think about this one, G-type phonon and F-type phonon. There exist 2 types of phonon scatterings, and yes, we have many different branches originated from detail of our EK relation. However, I wanted to say that although we have at least 6 different branches of our phonon scattering, which one is the most important one? Then my clear answer is this guy is the most important one. G-type phonon, whose energy difference is about 60 milli-electron volt. That is the most important one. How important is it? Roughly speaking, almost half of our inelastic scattering is originated from this 60 milli-electron volt LO phonon. And when we consider, so now say that we have all of due of scattering mechanisms, then there are phonon mechanism, phonon scattering, and others. So we will study later. And inside, even inside in this phonon scattering, we can divide once again in elastic one and here elastic one. As I told you before, in terms of momentum relaxation, actually contribution of this elastic scattering is quite high, about 50%. And now in this 50%, remaining 50% of our elastic scattering, momentum relaxation due to the or energy relaxation due to this inelastic scattering, we can also divide them into 6 different cases, but here LOG phonon is dominant and its contribution is also about half, and all others. So when means that the researchers previously 30 years ago, 40 years ago, when they model the phonons inside the silicon system, they as their first choose, yes, so LOG phonon was taken as the representative mechanism to relax the energy. And of course, you must consider elastic scattering too. Without this one, then your mobility value will be highly overestimated, because momentum is mostly dominantly relaxed by this elastic scattering. And where can you find the elastic scattering? Oh yes, we can find G-type phonon, F-type phonon, but where can you find the phonon whose energy relaxation is almost 0? Yes, you can find somewhere here. In this case, they have almost 0 energy, and they have quite small values, small k values. So actually it is something like just happening inside, only inside your belly, because in order to have almost 0 energy, then your k value should be also quite small. So therefore it does not provide sufficient k values to escape from one belly, your original belly. So now let me just make a summary for this phonon discussion. You may consider 3 different types. One is just intra means that internal, intra belly scattering. Usually this intra belly scattering is regarded as elastic scattering, and also it is related with the phonon called as acoustic phonons. They are fast, yes, they are fastly moving phonons. And now we can think 2 other types called as G-type and F-type. Both of them are characterized as interbelly scattering. Here interbelly means that it starts from one belly and moves to the other belly, and depending on the final destination belly, we can divide them into 2 different ways, G-type and F-type. Yes. So in the case of G-type, the degeneracy is just 1. There is only one destination. However, in the case of F-type phonon, how many destinations can you find? There are 4 copies of bellies you can arrive. Starting from this one, okay, you can go to that way, another one, another one, another one. So we have 4 different choices. So maybe some of you feel that this discussion is quite long. Why we are spending so much time on this stuff? It is closely related with the magic of strain engineering. How can we improve the mobility of our silicon conduction band, our MOSFET? How can we increase the mobility of our MOSFET? That is related with this band structure. So we must understand this band structure in order to find out or understand the way of strain engineering. Okay, so unfortunately all of our discussion is limited to the conduction band. For balance band, we have to also consider different band structure, because in the case of balance band, instead of this 6 minima called as bellies, we have heavy hole, light hole, and split op hole. However, I think that just for this course, just stay here. So if you have any question, then please let me know. So now, oh yeah, please. Okay.
그 F 타입 스캐터링에서 맨 아래 있는 좀 걔가 TO 폰이 아닌지.
So
전 슬라이드에 보면은 TO가 이제 에너지가 LA 폰은 에너지보다 높은 걸로 보이는데요.
So
에로 F가 아니라 TOF.
Okay, so right now I cannot exactly remember, so please let me have a time to check the reference. So that was a really good question, but unfortunately I don't remember exact numbers here. I just took it from the reference. So after the session is over, I will come back to my office room and check my table. So thank you. So your question was related to this one, whether this is correct or not. Okay, so thank you and good question. Then please ask me questions if you have any ones further. Okay, so now now we are talking about the temperature and doping dependence. But please note that up to now we have considered the scattering by phonons here. Phonons. It means that even when we have perfectly pure silicon, but this phonon scattering will exist. However, other ones like for example due to impurities or other mechanisms can be eliminated, because this is all related with the imperfection of our system. However, even when we have a perfect crystal structure, in that case our phonon scattering will exist. The only way to kick out the phonon scattering is reduce the temperature. If you reduce the temperature, then phonon is just thermal vibration over your crystal lattice. So if you reduce the temperature, then the degree of their thermal movement will be significantly reduced. So interaction between your electron and thermal vibration will be reduced too. So what we can think is temperature dependence of phonon scattering is directly related, directly observed. So where can you find it? So this is the Celsius scale, and we are somewhere around here, living here. And when we go to lower temperature, then you can see that, for example, starting from, for example, this one, whose doping density is quite small, 10 to the 14. Actually, 10 to the 14 is really difficult to make. So even if you try to buy a wafer which is not doped at all, but typically you can get the values like 15, and that is the minimum value. So this is special one to make an experiment. After that, when you cool it down, then you can understand the mobility goes up, significantly goes up. Yes. So we are now saying that electron conduction band can have about 1400. However, this is only related with 300 Kelvin. If we cool it down, then it can easily exceed the values like 2000. Yes, it depends on the case. And now let's consider doping dependence. Up to now we have considered phonon. However, let's think about this one. Fortunately, you have made the doping density like 10 to the 14. Great. Then how can you measure the mobility? In order to measure the mobility, you need carriers. However, number of carriers is directly related to the doping density. In this case, in order to get good high quality silicon structure, you just reduce the number of charge carriers. So there are not many carriers, so it is difficult to detect its electrical signal. So for example, compared with 10 to the 14, so the doping density 10 to the 19 will be 100,000 times more electrons inside it. So its electrical signal will be also such a times higher. So it is easy to detect the electrical signal. I mean, the electrical signal means that the current. In this case, if we have 10 to the 19, then this is just slightly above 100. This is 200, therefore this is just 100 something. And just by applying the doping, your mobility, starting from intrinsic mobility like 1400, now you have just 100 something. So almost 10 times of reduction in your mobility. So mobility is really a difficult quantity to improve. That is really difficult quantity. And now if we cool it down, then it is also increasing. But maybe you feel something different. When you cool down the sample with 10 to the 14 per cubic centimeter, how about the increasement of your mobility? Here you have significant increase. Please note that this is also written in logarithmic scale. So this small change in this graph shows exponential increase. However, you may see that in this case, 10 to the 19 case, it is not that high. The degree of mobility improvement is not that high. Why do we have such kind of differences in their behavior? Please, it is only because in this case, in this 14 case, actually the mobility we are observing is dominated by phonon. However, in the case of this 10 to the 19 case, there are two competing mechanisms, phonon scattering and the scattering due to impurities. When you cool it down, you can easily understand phonon scattering will be diminished significantly. However, even in the case, impurity stay there. So now from the only slight improvement of your mobility when you cool down your highly doped sample, then what we can say is for highly doped sample, the mobility is more or less dominated by the impurities, not phonon. Okay, then how can you model these competing mechanisms? For example, mechanism A, mechanism B, mechanism C. They are contributing different scattering mechanisms. For example, let's say that once per second, 10 times per second, 100 times per second. Let's just make a beat. And there are 3 guys. And one just say that once in a second. And this second guy said that this is third one. I cannot follow this quite a fast manner. But anyway, in that case, each of them makes some beats, and please try to estimate the overall effect out of these 3 contributions. What is the dominant one? The dominant one will be, of course, by number C, symbol C, because it is most frequent. So simply speaking, phonon scattering is just scattered in that way. And impurity scattering, then what will be the dominant scatterer? Then impurity. Then how can we model this overall effect out of each contribution? For that case, usually we make this kind of thing. Each of them, mechanism A can have typical time for scattering tau A, for example B, tau B, C, then tau C. Then which one will be the most influential one? The one having the shortest time scale will be the dominant one. So what we do is, instead of summing them all, then when we just summing them all, then actually the A, which has the longest time constant, will dominate. Instead of that, we just make a sum of their inverse relaxation time. Then what will happen? If you make such kind of manipulation, then which one is dominant one? The one with shortest tau value, shortest relaxation time, will contribute dominantly to your overall total relaxation time. So also please note that what was the assumed relation? So mobility was assumed as Q tau divided by mass. So when we are considering the same material, mass is the same, so tau is proportional to the mobility. So roughly speaking, instead of this kind of inverse sum of relaxation time, for example, we can say that inverse of mobility can be obtained by one mobility dominated by or restricted by one scattering mechanism, and another scattering mechanism, and another scattering mechanism. We can make it that way. I mean that, simply speaking, when we have phonon scattering and impurity scattering, then in following this modeling approach, we just try to phonon limited mobility. and we just try to model impurity dominant or impurity limited mobility, and by taking this relation we can estimate the overall mobility out of this system. If we had third or fourth scattering mechanisms, we just add them up in this inverse sum scale. That is actually it has its own name. It has its own name, and it is called as Matheson's rule. But we yes, I think that understanding this Matheson rule is okay, quite good, but we have to also understand this is not very exact. I mean that in practical purpose we may always rely on this relation. However, if we go to the microscopic description about electronic gas, then actually this is not the case. It is because when you try to calculate tau, it is always related with some average. Sometimes you may have the difference between first take average and do something, or do something after that take average. For example, let's think about this one. You may have the average velocity, and average velocity can be squared. It's possible. However, you may have a similar quantity like first take the square of your velocity and take its average. Seemingly they should be the same, however in reality they are not the same quantity, and usually what is we call the difference between this quantity and that quantity as a, we have name, variation. In statistics, when we have a certain quantity takes not variation, sorry about that. When you take this operation, that is defined as variance over a variable A. So as you know, always they can be different. Quite similarly, in this case, our tau, relaxation time, is once again just averaged value. However, in order to calculate the mobility exactly, first of all we have to do something after that takes the average. But instead of that, our available quantities, each individual tau, they are already averaged quantity. So that's the reason why Matheson's rules is not exact in macroscopic way. Some authors, even researchers in the real field, submit a paper to me and containing just Matheson's rules applying in a microscopic, and it is rejected because they misunderstood the microscopic nature of this property. However, in a practical sense, you are almost always allowed to apply this Matheson's rules. Okay, thank you for your attention and see you next Monday.